Hello guys, this is a continuation of our previous solution. In the previous solution we solved this problem number 2, in which we were given an insulator with a cavity and we determined the onset of partial discharge for this cavity, and we found out that the relationship between the applied voltage UA and the voltage across the cavity UC was given as E plus CB divided by CB. And the CC is the capacitance of the cavity, CB is the capacitance of the healthy insulation in series with the cavity. If we rearrange this equation, the voltage across the cavity UC is equal to UA multiplied by CB divided by CC plus CB. And in the previous solution, we calculated the values of CB and CC, and if we plug those values, we will get 1.CB divided by 1 plus CB divided by CC plus CB. We will get it equal to 1 over 1.5 and multiplied by UA. Okay, so that will be our UC. Again, UC will be equal to 1 over 1.5 times UA. Based on the calculated results from the previous example, we can find these values. And from the graph, our cavity is lying at 1.013 bar, and the spacing between the electrodes, or spacing between, or the gap spacing is 1 millimeter. So if we calculate PD will be equal to pressure multiplied by the gap distance. So we will get 1.013 bar mm. Okay, and we will find the value for this point. We will find the value of breakdown voltage for this point. We will get approximately at here. Okay, so which is 4.5 kilovolt. What is this? This is the breakdown voltage of the cavity. Okay, or where the cavity collapses. So we call it UCI, onset voltage, or the inception voltage of the cavity. This will be equal to 4.5 kilovolt. Okay, and so we will use this information to solve another problem which is given now. Now we are given the system for problem 2. The system for problem 2 has frequency of 50 Hertz and voltage supply of 6 kV RMS sinusoidal, and pressure in the cavity is same as before. Breakdown voltage in the cavity obeys Paston's law, so breakdown voltage will be the same as we calculated earlier in the previous problem. Now we are given extinction voltage. Okay, so extinction voltage is the voltage level where the breakdown ceases, where the breakdown stops in the cavity. Now we need to draw the voltage waveform and calculate the steady state partial discharge frequency. Partial discharge frequency means how many partial discharge pulses occur in 1 second. So first, we will find how many partial discharge pulses occur in one cycle. Then we will multiply it with the frequency of our power supply. So that's how we will get the frequency of partial discharge pulses. So now, again, so we are given this information, we are given UCI, and also we are given extinction voltage UEI, which is equal to 0.5 kilovolt. Okay. So, and the applied voltage U of t is equal to square root 2 times the RMS value URMS and sine of omega t. That's our applied voltage. And URMS is 6 kilovolt. So we can write it square root of 2 times 6 times sine of omega t, and units are kilovolt. Okay. Now this will give us 8.5, approximately 8.5 sine omega t kilovolt. Okay. Now what will be our voltage across the cavity? What will be the voltage across the cavity? So voltage across the cavity is, you can see from this relationship, UA divided by 1.5. What is UA? UA is the applied voltage. So whatever voltage we are talking about, this is UA. This is UA. Okay. So UC as a function of time will be equal to UA function of time divided by 1.5, and put the values and we solve it. Put the value of UA 8.5. So 8.5 divided by 1.5, we will get 5.66 sine omega t. Now our applied voltage has a peak amplitude of 8.5 and our voltage across the cavity is 5.66, and we know that the cavity collapses, or the cavity is discharged at UCI of 4.5 kilovolt, which we found from the Pascal's curve, and the extinction voltage UE will be equal to 0.5 kilovolt, where the discharge stops. Okay, so now we need to draw the pattern for the partial discharge activity. In order to draw the pattern, first we are gonna plot UA. First we are gonna plot UA, then we are gonna plot UC. Okay, so this is done here. Okay, so UA has a peak amplitude of 8.5, as we saw. So UA has a peak amplitude of 8.5. So you can see a sine wave whose amplitude is 8.5. This is 8. So whose amplitude is 8.5. Then UC has an amplitude of 5.66. So you can see here UC, which is this waveform, has an amplitude of approximately 5.66. Okay. Now, in order to draw the partial discharge characteristics, how partial discharge behaves, So we will follow UC curve. So voltage will rise across the cavity. Okay, voltage will rise across the cavity until the voltage reaches 4.5. So this red dotted line is in fact the UCI, which is the inception voltage across the cavity where the partial discharge occurs. And this blue dotted line shows the extinction voltage level where the partial discharge ceases or partial discharge stops. So now here our cavity will collapse. As cavity collapses, we will have voltage drop, and voltage will drop until it reaches the UE or UEI, until it reaches the extinction voltage. Okay. Now here our voltage was 4.5. Now we came from 4.5 to zero point 0.5 volt, as this UEI is zero point 0.5, which means our waveform, this UC waveform, is shifted down by how much? By 4 volts, 4 kilovolts. Okay. So now our voltage will start to rise, but now as the waveform is shifted down by 4 kilovolt, so now our waveform will achieve a maximum value of 5.66 minus 4. So 5.66, this was supposed to be 5.66, but now because it is shifted down, so 5.66 minus 4, so that will be 1.66. So now this waveform will only achieve this much value, and it will follow the same pattern. Okay, then it will go down until it reaches the breakdown voltage on the negative side. It is the ionization voltage on the negative side. Okay, and then it will collapse, then it will start to rise again. Okay, then until here it will collapse again, then it will go down. Okay, then it will again rise like in the positive cycle, then it will go to here, then it will collapse here, and then it will go down. Okay, so this is how the partial discharge will happen. And now we can count how many pulses we can see. 1, 2, 3, 4 pulses in one cycle. Our power cycle started from here, went all the way, and then it completed one cycle, completed here. And in one cycle we have 4 pulses, and so the frequency of PD will be 4 times the frequency of our power supply. So it will be 4 times 50, so we will get 200 hertz. Okay. That's all. Thank you.